Por favor.
Valeu, Rogério.
Pode começar.
Valeu. Bom, boa tarde. Bem-vindo a todas e todos. A gente está começando aqui o seminário que a gente está chamando de a série Quest, né, que é de um projeto que é Sistemas Quânticos Efetivos e sua termodinâmica, né? E, bom, esse é um projeto financiado pelo CNPq, um projeto universal, e tem participação de pessoas do México e do Reino Unido, e, portanto, eu vou mudar para o inglês. Okay, so it's our great pleasure to have Guilherme de Souza for our kickoff meeting. Guilherme did his undergrad in São Paulo at USP São Carlos, where he did like an internship with Frederico Brito, who is part of our project. He's a member of our project, and also he's actually visiting me. He's here. So we were very happy to see this article that came out in PRL by Guilherme, and we decided then to invite him. So he's now doing his PhD under Professor Jarzynski, who is a very well-known name in thermodynamics, statistical physics, and quantum thermodynamics as well. So we're very happy to have you here, Guilherme. Please.
Yeah, thanks, Fernando, for the nice words. Also, thanks, Fred, for inviting me. I was actually very happy to know that there were people interested in my work. So for me, it's an honor and a pleasure to be here. And before I start, let me just mention that, feel free to interrupt me at any time. There's some technical details on the slides. I hope that's not too heavy, but if you have any questions at any moment, please interrupt me. So yeah, let me get started. And before I actually go through the slides, let me acknowledge the people that helped us and was part of this project. So we had people from the Lund University, so Bjorn, Farage, and Peter, and people from University of Basel, so Patrick Potts. So they were the mainly contributors and the actual people that drove this project. So we thank them then very much. I also want to thank you, my colleague, the bunker, and my advisor, Chris Jarzynski, for the support and help through this project. So before we actually dive into this, let me mention a few motivations of why basically this is interesting. And these motivations, I try to put them in three slightly different but also overlapping categories. So we have a technological motivation in the sense that recently, in the past few decades, there has been a lot of interest in quantum technologies. A lot of techniques and platforms were developed, and we're much interested in to help and develop frameworks to study them. There's also the scientific motivation in the sense that all this work that has been developed, and the framework that we're trying to study here is based on what we are calling here a quantum control, which is basically the fact that we have some system, we're trying to measure it, and based on the measurement, we're applying some sort of feedback to achieve some particular task. And all this is tied to some very scientific questions. For example, the Maxwell's daemon, where we're trying to convert information into some useful work. We're also trying to develop some general framework for measurement and feedback. We're trying to use this framework as a playground for asking quantum thermodynamical questions, and also in a sense fill the gap between the theoretical models and the experimental implementations. And there's also at least, but the last but not least, the engineering motivation, in the sense that maybe with these frameworks, you can help to improve the parameter tuning for protocols, and also investigate some new protocols, and maybe help improve the existing ones. So for this talk, I separated in three parts. So the first, it's a more basic level description of what I mean by the model of the measurements I'll be considering here. The part 2, I'll briefly outline the steps in the derivation of our quantum Fokker-Planck master equation, and which is the main result that we had in this PRL. And it's the part 3, I'm going to mention some of the toy models and applications of this Fokker-Planck master equation. So first, before we actually dive into this and explain the relationships between measurement and feedback, let me back up a little bit and talk about what we understand by a measurement in quantum mechanics. And from that, I'm going to use the super standard Stern-Gerlach experiments that we all learn in the introductory level quantum classes in our physics degree. So what happens is we have some system here. It's an electron. They have spins. I'm gonna interact to this magnetic field, and depending on their spins, they're gonna feel this this disturbance, which we're gonna deflect the trajectory of them. And this basically is a physical implementation of the measurement problem, in the sense that for a quantum system, even if we start in a superposition, there's some coherences. Once we measure in a particular basis, let's say up and down basis, the outcomes are going to be stochastic, in the sense there's a probability associated to finding a spin up, probability to finding a spin down. But once that is done, the system collapses. So there's the famous wave function collapse, and after that, all subsequent measurements are going to give you the same result. So in a sense, this is this causes a very large disturbance, but we also get a lot of information, because once the experiment is done, we know exactly what the state our system is. But we don't exactly want that, in the sense that this is too much disturbance for the purpose of what we want to do. So here we're gonna try to develop a framework. Actually, this has already been developed, but the point is that we're gonna use the framework called a weak measurement, in the sense that we're gonna get less information, but also cause less disturbance in the system. And the intuitive picture to understand this is, again, let's continue using the Stern-Gerlach experiment. So the usual setup of the experiment, we have some continuous degrees of freedom, spatial degrees of freedom. They're, for example, for simplicity, imagine they're independent of the spin degrees of freedom. They're going to interact with some magnetic field, and the particle is going to feel a deflection. Let's say deflection towards let's say this is the z-axis, so positive values of z when the spin is up, negative values of z when this is down. And the point is that this is projective, in the sense that if we measure the position of the particle to be somewhere in z positives, we know that our particle has spin up. If we measure z to be negative, we know that the particle is in spin down. So this is a projective measurement. We get, again, a lot of information, but there's also, we destroy all the coherences between our system of interest. But then what happens if, instead of doing that particular setup, we measure, we create a setup where now our two distributions of particles being up and down, they have a very large overlap. In contrast with the previous picture, where they were very, essentially you had a very nice experimental resolution, but now this resolution, you don't have it anymore. And the sense is that now, if you measure your, coordinate z to be somewhere here, you basically has, no way to say that the particle is either up or down. So in a sense, you are getting less information, but you're also not destroying the same amount of coherence. So you're, in a sense, doing a weak measurement, because you're disturbing less your system. You gain some information. Maybe on average, you can tell where, if the particle is more into the up state or down state, but you cannot say for sure what is the state of your system. And we can, generalize that using this, pointer-based models. And that's basically the von Neumann model for weak measurements. And we can basically generalize that for any particular, any arbitrary operator, not only, sigma z with two eigenvalues. So here we start our system coupled to this pointer state. This is going to evolve, and it's going to get some shifts depending on the values of the depending on the eigenvalues of the operator you're measuring. So the point is, the area under these curves, they're going to give you what is the probability for these measurements to occur. So basically, quantum mechanics 101 in terms of projective measurements. And then this is a very nice playground, because here we have this parameter lambda that basically controls your experimental resolution or your strength of the measurement. And when you have this parameter to be very large, which is more or less what's being shown in this picture, then you have a very strong measurement, because basically you can say, if you measure your position to be here, you know what state you are. If you measure your position to be here, you know what state you are. But what happens when lambda goes to 0? And that's the weak measurement situation, simply because now, instead of having 3 different or n different Gaussians that they are very spatially resolved, now we have more or less a single Gaussian, basically centered on the expectation value of that operator, but we can no longer resolve the outcome of the measurement. So in that sense, we are getting way less information. We don't know what is the state of the system after the measurement. We only get a partial information about that, and this partial information is that we get the value of the average value for the standard deviation.
Excuse me?
Yes?
In the previous slide, what is lambda? Do you have it in the equations? I cannot find it, or in the picture?
Yes. So yes. So here lambda is basically the parameter that controls the spread or the standard deviation of the Gaussian states for the pointer. Yeah. So I mean, lambda is not a parameter. It doesn't appear here, but it's encoded in this wave function theta of t.
Okay. Thanks.
More questions on this? Okay, actually, in most parts of my slides, there's some technical details, but I'm trying to keep it more simple and skip some of them. But I mean, feel free to ask me at any point. So now the point is that we have this recipe to describe a weak measurement. It's just that we have to consider very spread Gaussian pointers. And there's a very well-known recipe in terms of POVM, so positive operator valued measurement, that basically can gives us this the generalization of this for arbitrary initial states. And what happens is that now we can see that the outcomes of the measurement, which in the previous situation was a variable that so in this situation, the outcome of the measurement is a variable that is a stochastic variable, because outcomes of quantum measurements, they are stochastic, but the probability distribution function follows these curves. But now, since we have this weak measurement, we have a single Gaussian. So basically the outcome of our variable is a stochastic variable that's being drawn from a normal distribution with very large standard deviation and centered more or less around the expectation value of the operator trying to measure. And that is fine. We are getting only a very little amount of information about your system, but we are also on the other hand, we are basically creating a very small disturbance. So what we can do now is that we can basically do this process every single time and define what I mean by a continuous measurement. So it's a very weak measurement, but made very often. So every interval of time dt, we make a very weak measurement that basically scales with dt, but these are done very very often. We can basically write the Born rule for how our state is updated after one particular realization of this experiment, and doing what physicists love the most, which is do some expansions up to first order in dt. We can basically get this equation that is called the Blavkin equation, which is a master equation for the evolution of the density matrix once we are doing continuous measurement. And what is nice to interpret for this equation is, so first this is an equation that is stochastic in the sense that every realization of your experiment, even if you start with the same initial condition, will give you different outcomes simply because they are stochastic and random, which means that the evolution of your density matrix is also stochastic. So here, instead of thinking about a deterministic evolution of your density matrix, you have to think about in terms of trajectory level evolutions of your density matrix. That's why I'm including this subscript C as a conditioned density matrix, conditioned on the outcomes that you get from your measurement. And the ingredients, the terms that appear in this Belavkin equation. So the first term is the usual unitary Schrodinger equation. The second term is a very important one. This is called a back action term, back action due to the measurement. And this D here is called, is usually referred as the dissipator. So what this term is doing, it's dissipating or basically killing coherences or, creating decoherence in your system in the basis of the measurement operator with rate lambda. So basically you're destroying coherence, the more you destroy, the more information you get, and vice versa. And this term is a stochastic term that arises due to the fact that the evolution of your system is conditioned on the outcomes, on the noisy outcomes actually. And before I actually continue, I just remember that I should point out that the outcomes of this measurement, they are, as I mentioned, they are centered around the expectation value of this operator. And because we have a essentially super large or infinitely large Gaussian, their spread is super large in the sense that this spread can be written in terms of a white noise, and white noise has kind of nice but also well-defined properties in the sense that a white noise, the average of a white noise is 0, but the second order correlation is a Dirac delta function. So it's kind of very hard to deal with this kind of noises. But that's fine. I mean, we are doing this framework for continuous measurement. We are making a continuous measurement, but what we can do with that continuous measurement. So as we allow our system to evolve and our measurement apparatus to keep measuring the system, we're getting like a time trace of the outcome of the measurement, and based on that we can apply feedback. And feedback here is meant to be understood as a feedback loop of this form. So you have your system, you make a measurement, based on the outcome of that, which is this variable z, you change your Hamiltonian. And this can be useful to apply tasks. So for example, depending on the if your system is in the excited states or in the ground state, you may tune your magnetic field to rotate your system in one direction or another direction. So that's why we want to apply feedback. But the point is, due to this ill-defined properties of this white noise, the only types of feedback that we can apply are linear feedbacks. And this is true because higher orders, they basically diverge. And here the second order already is a Dirac delta. But for the case of linear feedback, some studies have already been done a few decades ago, and actually we have already a master equation that can describe linear feedback with continuous measurement. And this is the Wiseman and Milburn master equation. So any questions so far before I continue? Okay.
I do have one. Sorry, it just took me time for unmuting. So in the previous slide, so if I understood it correctly, this equation is actually non-linear on the state, right? So this last term there, it's non-linear, but that's due to this kind of normalization that you have to do at every time step, I suppose. Right?
Yes, precisely. Yes. So yeah, I forgot to mention, but yeah, as you mentioned, this expectation value is what makes this equation non-linear. And because basically average of A here is trace between A and row C, so it's an average conditioned on all the previous values. But yeah, you're correct. So this is a non-linear equation in the sense that yes, you have this nonlinear dependence, and that arises from the fact that you have to renormalize your density matrix every
Right.
step.
But my question is actually, so when you go to these other equation now where you have feedback, so if I'm following correctly, what you're doing is kind of on the top of this continuous observation, you're putting also feedback. And this one, I think it's linear, or am I missing something?
Yes, I mean the feedback here is linear. And yes, so the point is that to get into this master equation, so why, I mean, I think I understand now your question. So why is this equation non-linear on the density matrix, and why is this equation linear? Because this equation, rho here is a average rho, in the sense that you're not focusing on particular trajectories, but what is the, once you repeat your measurement many times, and once you run your experiment many times or in many copies, what is the average evolution for the density matrix? Okay. So that and I mean the same way that you can get a linear equation by averaging over the noise, which basically will kill this term. Then you get a linear equation in rho. You can do the same and derive linear equations if you average the noise with feedback.
So the previous one is then for a single trajectory. Is that the case then?
Yes, that's correct.
So may I interrupt you? Sorry. But in this Bělavský equation, if you make a mean of this equation, you have the mean of A minus the mean of A. So you have this term 0, right?
I mean, to get actually, mean of average or expectation average of A here, you would need to take a trace. But to get, the average over many realizations, you actually, apply a expectation, sorry, not expectation value, but ensemble average over many realizations of the noise. And that ensemble average basically hits this term, which is, ensemble average over a Brownian particle, a Brownian noise, and that is 0. So that's why you get rid of this term in the ensemble average of many realizations of the noise.
Just to see if I understood correctly, then, so the average would be in different rows, so to say, right? I mean, then you would have the average over row C, where this average which is there is already for a fixed row C.
Yes. So what I mean by that, let me see if I can get my pen. Something like this. So I apply some sort of expectation value over the noise, and here the noise is being denoted by W. So it's expectation over row C. And so it's a little bit hard to draw here. So expectation over many realizations of the noise for this condition density matrix is what I'm calling this new density matrix, or you can call it an average density matrix. And the properties of the noise is that average over many realizations of the noise is 0. The same way that for a white noise, the average of white noise is 0.
Thank you.
Okay, more questions on this? Okay, so thank you for the question. So to clarify here, so this is the over many realizations of the experiment. This is what happens with your quantum system once you're applying this continuous monitoring and feedback. But so that's basically where our project starts, because all of that was already being developed decades ago. So the first thing that we noticed is that one of the reasons why it's hard to apply feedbacks more general than linear feedback is because the noise is so noisy, in the sense that the noise is dependent on a white noise, which is very ill-defined in that sense. So we had the idea, so what happens if we filter that noise? And why we want to do that? So there's two reasons. So first reason is that we can maybe clean up a little bit our measurement outcome, which might help us apply more precise measurements, because we are not applying now measurements on the noise, we are applying on the actual real data and the interesting data. And there's a experimental reason why we want to define a filtered outcome of our measurement, because in reality, any real experiment has you know, a finite bandwidth, in the sense that any experiment cannot keep up infinitely fast with, you know, the signals of your system. So any real experiment will have, you know, in there, when you're plugging some cables, you're doing some experiments. I'm not experimentalist. I don't know exactly how that works, but I mean, people told me that in any real experiment, you have some finite bandwidth. So in a sense, some of your noise has already been filtered by the experimental apparatus. So that's what motivates us to define this outcome D, which is, you know, the basically exponential average over past values of Z, and that can be, you know, intuitively thought, you know, from this sketch. So imagine that this blue curve is the super noisy variable that's been evolving with the system, and now once we start applying the feedback, sorry, once we start applying the filtering, the larger we, you know, can keep up with that signal, so larger values of this bandwidth parameter gamma, we are getting closer and closer to this noisy signal. But if our detector is somehow slow, we're, you know, doing an average, and we're only getting, you know, trends of the values that that we're getting. But that's super nice from the, you know, theoretical point of view, because this signal is very hard to work with because it's not even continuous. But now D is a continuous function. It's discontinuous on its first variable, but that's, you know, already fine for us, because now we have a continuous variable that we can use to apply feedback. And now, you know, the properties of this D signal are not, you know, no longer ill-defined, so we can apply higher order feedback. So we can apply, let's say, quadratic feedbacks, or in principle any sorts of feedback, just because we're getting rid of the, you know, the super noisy parts of our measurement signal. So that's basically you know, the key feature of our model. And so now what we have, before actually getting into the results, let me explain quickly you know, some of the steps to derive our Fokker-Planck master equation. So now what we have is, for the trajectory level, is the Belявkin equation coupled to the evolution of this signal. So again, we have the Belявkin equation where now our Hamiltonian can depend arbitrarily on this parameter D, okay? And the evolution of D follows like a Ornstein-Uhlenbach process, or basically a Brownian particle around the average value of A. So basically, what is going on the variable D is that D drifts towards the value of A, but there's a little bit of noise. But this noise is, you know, much more well behaved than the previous case with the variable Z, which, you know, depend on the white noise. So basically, at the trajectory level, what you can do is to solve this coupled stochastic linear differential equations. I mean, linear, but there's a caveat that there's this nonlinearity here. But the point is that you have to solve this for one realization of your experiment. If you are interested in different realizations of experiment, you actually have to solve these coupled equations again and again, and maybe take statistics from that. But so again, looking at this equation and, you know, getting some you know, some ideas from classical mechanics, like the Brownian particle, and how the Brownian particle is related to the Fokker-Planck equation, which describes.
Sorry, Guilherme,
Yes.
Can I ask you a quick question?
Mm-hmm.
Can you just explain why? So the DW in both equations is the same DW, like each step is exactly the same noise in both of them, or it's like different DWs?
Yes, they are the same noise, because they basically came from the same noise source, which is the measurement.
Okay. Can we see that somewhere? Like, is there like an equation where I could see?
Yes. So first of all, this DW here, it comes from the Belявkin equation, so it's defined this way, and you can see kind of directly from this equation, because, you know, again, the way you construct the Belявkin equation and this noisy variable is such that you already get, you know, the same noisy for the variable Z and the variable rho. So then what happens is, when you define D in this way, and then you take the first derivative of D, and, you know, substitute what Z is, then you basically get this with the same noise.
Right. Sweet. Yeah, that makes sense. Thank you very much.
Sure. More questions on this?
Actually, just to, now that we start on this, so in the next slide, so this average on A is actually average of AC, or is
Yes,
that?
yes, sorry.
Okay,
Yeah,
thank you.
yes, yeah, it should be
Thank
average of AC, yes. Yes, so now the idea is that, okay, we have this, but we don't want to focus on, individual trajectories, but because, from the theory point of view, that's kind of hard to work because you basically rely only on numerical simulations. So what we want to do is maybe to get a ensemble picture out of this, the same way that from Brownian particle we go to Fokker-Planck master equation. Maybe there's a way to go from Belavkin equation to some sort of Fokker-Planck equation in quantum space. So what we do, I'm gonna skip here so I can focus more on some of the later results. So I'm gonna go quickly here, but the outlines of the derivation is that for every trajectory we have a rho c and a particular value of d at time t. So what we have is we construct this new object, which is a rho c of d, which is neither a probability density function, probability density distribution, or a density matrix, kind of a joint object, and it carries information on what is the value of d and what is the density matrix you have. So what we do here is, we follow very similar steps that you can go from Brownian particle to the Fokker-Planck master equation, but in this modified space. If you want, I can go more careful with more details on this, but we have to use some properties of stochastic calculus, like there's some identities, especially in the when taking derivatives, that are slightly different when you're working with stochastic calculus, but basically it's very similar steps that one can use to derive the classical Fokker-Planck master equation. But now you just have to be careful that here we have operators, they sometimes not necessarily commute, stuff like that. But in the end, for this object, which basically describes a density matrix average over many realizations of the protocol, so basically gives us some information about the quantum dynamics and the distributions over d values, because as I mentioned, d is a very stochastic variable. So at time, imagine if you always prepare your system with the same initial condition, run the experiment for 1 second. If you run the experiment 100 times, maybe in all those 100 times, you're always gonna get different values for d at the time t equal 1 second, simply because d is a stochastic variable. So, there's randomness associated with. So, if there's multiple values of that, we can, instead of thinking in terms of, specific trajectory values of d, we can think in what is the distribution of probability. So what is the probability for d to be, around 0.8 and 1.1? What is the probability for d to be negative? Stuff like that. So, we can do that. And in the end, take some average, because we're interested in the ensemble description. And basically we get, our main result, which is the Fokker-Planck master equation. So the Fokker-Planck master equation contains these two terms as, very similar to the Belavkin equation, and these two additional terms that they are kind of, Fokker-Planck equations. So that's what that's why we call it a quantum Fokker-Planck master equation. So before I actually, explain it more in more details, does anyone have any questions so far?
Just a question. I'm no specialist in this. I just remember many years ago, I seem to remember there was a big debate when people were discussing this thing of how, if you could be sure that this would keep the evolution positive, or even completely positive, actually.
Okay.
And there was some of these stochastic master equations that seemed reasonable, but there were huge fights because people thought they were reasonable, but then someone proved that they would make a density matrix become non-positive over time. So can you check for this kind of thing?
Yes, so there's a couple of things. So the first thing is that I think it's kind of proved that, any master equation, if my master equation was only these first two terms, this is a unitary dynamic, so positive, and this is a dissipator, so it can be written in the link platform. So these two terms, they preserve the positivity.
Yeah.
For these two other terms, honestly, I don't have a concrete answer right now, especially because, when you think about completely positive, you actually think in the, I mean, if you couple your system to any other, larger system, that should still remain positive. I don't have like a very rigorous mathematical proof that this equation should remain positive, but also, remember that this quantity is not exactly a density matrix. So I'm not sure if that necessarily has to remain positive always, because this is not a density matrix. If you take the, if you average over all possible values of D, then you get a density matrix. Then that should be positive. But honestly, at this point, I don't have a concrete answer if that is the case. Okay, more questions? Okay, so let me go, quickly through all these different terms in the Fokker-Planck master equation. So as I mentioned, before, let me quickly remind you what is the different parameters in our model. So A is the measurement observable, so the observable that we're doing continuous measurement. Lambda is the strength of the measurement that basically controls how much back action and how much information you're getting. And gamma is the detector bandwidth, or in other words, how fast your detector can keep up, and also, what is the lag, in a sense, your detector has with the actual signal. So the four terms in the Fokker-Planck master equation. So the first term is the unitary evolution, but also that can be generalized for any Lindblad evolution. There's a explicit D dependence because you can apply feedback based on D, and this can be very general feedback at this level. Here we have the back action that we discussed before, so that causes the system to lose coherence in the measurement basis. And these are the new terms. So this term, just like a Fokker-Planck equation, this basically describes a drift term. And this is a drift because basically D follows the evolution of the average value of A, and this is a diffusion. And there's diffusion simply because the evolution of D is noisy, and the trajectory level, it's unpredictable in a sense. And also, it's going to be important later, but the ratio gamma over lambda, in a sense, controls the diffusion parameter. So how much that diffuse, it's controlled by the ratio gamma over lambda. Okay. So also in that paper that I highlighted in the previous slide, we showed that in some particular cases, in this particular separation of timescale where gamma is much larger than omega, we can trace out the degrees of freedom of the measurement. In other words, we can average all possible values of the measurement and actually get a master equation only for the system of interest. Okay, so any more questions about this, about the Fokker-Planck master equation or the framework in general?
Guilherme, these derivative over the detection there in the last two terms, right? So these are the detection outputs, right? So these D there. So it's, yes. I mean, I'm just a little, this kind of details that's maybe much easier if the author explains than reading the articles, right? So how do I actually do that? Do I need like a functional form of rho? I mean, how to do this?
Yes. So the point is that, so here, I mean, the same way that from Brownian particle, we go to Fokker-Planck master equation and Fokker-Planck equation. And in Fokker-Planck equation, we have, first derivatives. So that's why we have, these D derivatives. Okay, that's fine. So, I mean, as you mentioned, you basically have to find what is the, rho dependence here and, solve this equation. So at this level, this equation, I mean, it's very nice, but it's also because it's a coupled, it's everything here is linear, but you have this, D dependence and some, partial derivatives here. So in a sense, at the end of the day, you actually have to solve some partial differential equations. So basically what you would do, for example, is to imagine that you're studying a two-level system. So for a two-level system, your density matrix has 4 terms, right? So rho, the first column here and all the other terms. So each term in your density matrix, it's going to be a function of D. and you actually have to solve what is the dynamics of each terms and their d dependencies. So this is kind of yeah. So I mean, in that sense, you have to solve this kind of complicated system. But yeah, so at this point, rho is a function of d. You actually have to take derivatives over that.
Okay, but I mean, so like, could you just put, well, it's a second order, right? Partial derivatives.
Mm-hmm.
I mean, you need some information to actually solve this, right? So you need like the initial conditions and boundary conditions and things like that.
Yes. I mean, the initial conditions could be, for example, the initial state separable in, your detector initially to be, let's say, d equals 0, something like that. That'll be a Dirac delta. And what you're gonna see would be, very similar to a Brownian particle, that if you initialize everything in a delta function, you see a spread. You're gonna see something like this. So you have to solve these equations to actually find what aerodynamics is.
Okay, thank you.
Okay, but yeah, so thanks for the question. So, ideally, we basically switched from a numerical simulation at the trajectory level to a numerical solution at the ensemble level, where now we can. But now, the good thing is that ideally we can also get distributions over the outcomes of D, and maybe get statistics on that. But let me quickly go through some of the toy models we apply this. So maybe it's going to be more clear how we can even do some analytical calculations on that. So the first toy model in the paper is a classical toy model that might look like boring, but we got some intuitions from that. So what happens here is we have a classical 2-level system. It's coupled to some bath with some temperature T, and we are measuring sigma z. So basically we're measuring the population imbalance between the excited and ground state. So if you run the experiment, this might look like one particular trajectory. So for example, the particle is in the ground state. It gets excited because it got some energy transfer from the bath. It went to the excited state. Then maybe that excitation went back to the bath. It goes to the ground state again, excited states, and so on and so forth. So this is the system and the measurement operator. And what is the feedback? The feedback is an energy extraction feedback. So what we want to do is, if we see the system in the excited state, we basically change the Hamiltonian, instantaneously to extract that excess energy. And when we extract that, basically now the excited state gets mapped into the ground state. We wait again. Now the one state is the ground state. We wait again for another excitations to come from the bath into the system. When we see that our system is again in the excited state, we extract that energy again. So in the ideal operation of our protocol, we actually every time our excitations jumps into our system, we're extracting that energy basically.
Excuse me.
Mm-hmm.
The plot on the lower left, that is a schematic plot, or that is a plot arising from some equation?
Yes, that is a schematic plot.
Okay, thanks.
Yes. And so what happens is that, intuitively, it might make sense that we can we can extract energy from this single bath. So this are the results. So what I'm plotting here is the power extracted as a function of this ratio lambda over gamma. And there are some situations where I'm actually heating up the system, and that happens because in these situations where my measurement strength is so small, I'm actually getting so little amount of information, and so it's more noisy. And because it's more noisy, I'm applying the protocol wrong. I mean, on average, I'm kind of applying more wrong protocols than right protocols. So that's why I'm heating up the system. But if I have somehow intermediate levels or large values of my measurement strength, I can actually do this, run this protocol and actually extract some energy. So here's the power and the point. In here the dashed lines are calculated using so dashed lines were derived using analytical results in the separation of time scale limit, and these are in the solid lines are the numerical results. So even though the Fokker-Planck master equation might be slightly harder to solve analytically. In some occasions, for example, when you have separation of time scale, you actually might solve it analytically. So that is nice. I mean, we got a very cool result. We can extract energy, but this is classical. So some people might find it boring. So that's why we also considered the quantum version of that classical model. And for the quantum version,
before
yes.
you go into the quantum version, don't you have some kind of Maxwell-Demon situation there that you have to be careful with? Like you're extracting energy from a heat bath and you don't have a sink?
Yes. So, I mean, all these results here, I mean, we derive them using our equations, but honestly, we haven't investigated, that deeply the thermodynamical consequences of our results, and what do we mean to actually extract energy from a single reservoir. But our guess is that I mean, to actually run the experiment and collect that amount of information, there's an entropy cost to keep track of the measurement signal. So we're doing measurement. So I mean, in that sense, we are the demons. So the same way that the demon was resolved by introducing the entropy cost of erasing the demon memory. At some point, we have to think about that. But yeah, there's still some work to do on that direction.
Okay.
More questions? Okay, so in the quantum model, the idea is the same. So we have this this coherent drive. When the coherent drive makes this two-level system to get excited, we again shift the energy levels, wait again to be excited, and so on and so forth. So very similar idea, but now this is quantum. And because this is quantum, now the back action actually plays a very important role. In particular, there's this very intuitive phenomena that happens, which is the quantum Zeno effect, which happens to quantum system, which is basically if you measure your system too strong and too fast, you're basically freezing the evolution in the sense that you're always projecting in the one particular state. So the system doesn't have enough time to evolve. So you're kind of freezing out your evolution. So that's why for this quantum model, we have, instead of like a monotonic curve for the power extraction as a function of the ratio lambda over gamma, we have this optimal condition. And it's optimal because if lambda is 0, we're not getting any information at all. So there's no way we can apply this protocol correctly. If we're measuring it too strong, we're basically killing the coherences, and killing the coherences for this model means that we are also not able to extract that much amount of power. Okay, so for quantum systems, there's like a trade-off between how strong your measure, how fast you process, and also that basically affects the quality of the protocol you're applying. Okay, so more questions on this? Essentially, these are all the results that are present in the paper. Later, I want to briefly show some of the results that we're working right now. But for these slides, does anyone have any question related to this or any other topics? Okay, so quickly going through the last part of my presentation, let me mention a work in progress that we're doing with maybe the first or the second most favorite system for our physicists, which is the harmonic oscillator. So we already studied two-level system, they are nice. Now we want to study harmonic oscillator, which might be even nicer. So the idea here is that the task we're trying to apply is a cooling task, in the sense that we're trying to extract energy from a harmonic oscillator to maybe cool it down very close to the ground state, or maybe the ground state, why not? So the protocol we're trying to implement here is a protocol based on a position measurement. So we measure the position and basically shifts the harmonic trap into the position. So in a sense, we are always following the particle, trying to make it closer and closer to the bottom of the harmonic trap in an attempt to remove potential energy and cool down the particle. So again, we can apply our formalism into this model. And what is very nice to this model is that this is now analytically solvable. You don't have to actually assume anything about the initial conditions. You just basically have to solve the quantum Fokker-Planck master equation for this model, and you can derive what is the steady state average energy over many realizations of the protocol in the long time limit. And that can be done for arbitrary values of these parameters. And what is very nice is, again, the same way that we got a sweet spot or an optimal condition between the ratio gamma over lambda, we get that here. And so that tells us that we can actually cool down our system very close to the ground state, and the penalty that we pay is proportional to gamma over omega squared. So if we do things very, very slowly, we can basically get as close as we want to the ground state. Another very interesting result is that we can tweak a little bit our protocol to now implement both position and momentum measurements, and also apply feedback based on both. And we get a very, again, analytical results for this cooling task. And what is even nicer here is that we can get absolutely ground state cooling at the trajectory level. So now we don't actually need to make a bunch of measurements. If we apply our protocol for a particular trajectory, we're going to get ground state cooling. So that
here there is no heat path, right? I mean, you start in some like high energy state and then you cool it down, but the dynamics without this measurement would be unitary, right?
Yes, precisely.
But I mean, would it be possible to include a heat path? I mean,
yes, actually, yes. Actually, we have the results for the I haven't included them here. We have the results with the heat path, and what happens is that you can get, again, very close to the ground state, but there is some excess energy due to the bath, and that excess energy is basically proportional to the how strong you are coupled to the bath. So if the coupling strength to the bath goes to 0, you recover these results. If the coupling strength to the bath is somehow larger, than the measurement and feedback protocol, you're gonna get kind of a weighted average situation.
Right, I see. That's pretty cool. Thanks.
Yeah. So essentially, that's
Sorry, let me ask a question. Sorry, this average energy is very similar to the previous one, to the mean energy of the steady state, right?
Yes.
So I think that you can control the parameters and set one equal to the other. Is there much more than a coincidence, or it's only a coincidence?
I think at this point, this is kind of a coincidence in the sense that both protocols, they're quite similar. So this so this is so this first protocol is a moving X trap, and this is a moving both position and momentum trap. So they're very similar. So I mean, it's not super surprising that the results were quite similar. But what was nice is that by introducing this new measurement operator, it can do better than a single measurement operator.
Okay, thank you.
Okay, so let me quickly finish here my presentation. So I think I'm way a little bit more than my time. So the take-home message from this work is that you have to keep in mind that measurements cause disturbance, but we can actually control how much disturbance by applying a weak measurement instead of a projective measurement. And the outcomes of these measurements, they are stochastic. We can apply this stochasticity to investigate how our density matrix evolve. They evolve under stochastic master equation, no surprises there. And by applying this filtering, or basically getting rid of some of the noise, we were able to derive this Fokker-Planck master equation. And then we can use this to investigate situations of continuous feedback that can basically, for example, extract energy from a reservoir, or we can also cool down a harmonic oscillator to its ground state. And we also get a very nice intuition into the interplay of the roles of the lambda parameter and the gamma parameter. I forgot to mention, but quickly mention that hopefully there will be a preprint of these results maybe next month. So yeah, maybe stay tuned for that. And some of the next steps that we want to take on this project is maybe see if we can get some experimental verification of this model, and that will be a nice consistency check of if we're doing is actually a good model of the real experiment. Maybe we can help design new protocols or make the existing ones slightly better. We also have plans to maybe try to generalize this for arbitrary filterings. We want to investigate thermodynamics, fluctuations. There's also, some very interesting ideas on quantum information, error correction, shortcuts to adiabaticity that we can use in this project. So that's, with that, I thank you, and thanks again for everyone that came and all the questions.
Thanks a lot, Guilherme. Thank you for a very nice talk and very nice results as well. I'm sure there will be more questions. And I forgot to say, this as this is being broadcast in YouTube, so people at the YouTube, if you want to make questions, just write them in the chat and I'll transmit them to Guilherme. Okay, more questions? Please just open your mic and or.
So I do have a question, Fernando. May I ask?
Sure, go ahead. Carlos.
So thank you very much for the talk. I wanted to know, like, your equation, how linked is to a particular model, to a particular measurement model. Like you showed a model of continuous measurement. So yeah, that's the question.
Mm-hmm. Yes. So yeah, I think at this level we, at some point we also want to have some experimental input, in the sense that we want to actually check and investigate if our model for weak measurement is actually what the experimentalists are doing, because if maybe they're doing different models for continuous measurement, in particular weak measurements, then we might change. We might have to change our framework. But as far as as far as I'm concerned, the Belafkin equation, which is also which has also been derived in the context of weak measurement. It has been used for at least 1 or 2 decades. So I think at this point people might be happy and comfortable with working with this particular model for weak measurements. But honestly, I would like more experimental input to actually see if this is a real physical model for their experiment. It might be not, so we might have to change it for a more realistic model.
Thank you.
Gabriel.
Hey, Guilherme, if I can ask another question, I wanted to ask about the solution methods that you're using to compute these things.
Mm-hmm.
If you can go back real quick to the quantum Fokker-Pluk equation.
Okay.
Yeah, that one.
Yes.
No, sorry. The one where you have the screenshot of the paper. Yeah, yeah, sorry, that one was fine. Sorry, yeah.
Okay.
So what I was wondering is, can't you just discretize D over some grid? Like say take some grid of values and discretize D, and then you have one density matrix for each value of D, and then you just solve like a bunch of master equations in parallel. Isn't that simpler than?
Yes. So yes, good question. So I think that might be simpler, but honestly, I'm not sure if that capture all the physics that we're trying to to model here. Because, for example, the same way with because here the variable D, which is the detector outcome, it evolves like a Brownian particle, right? And the same way the Brownian particle explores the real space, D here explore the real space. Of course, D is in a real simulation, D is more or less localized around the eigenvalues of the operator A. Okay, but D can basically, move around in between. So I think you can do some kind of discretization in a sense that will be some sort of approximations. And that's, in a sense, what happens when, for example, you have some separation of time scale and you can do some, approximation. So what we show here, for example, is that if you have a separation of time scale like this, you can basically trace out D and solve a much simpler, master equation that now only depends on the each terms of the master equation. And in that sense, that's kind of a discretization of the D values. But I have the feeling that, depending on your problem and depending on the region of the parameters, maybe you don't have this kind of separation of time scale. If you do that, you might get wrong results simply because you're doing like an approximative solution.
Right. What is pi in this equation?
Yes. So I haven't explained exactly, but pi here are the they are the I forgot the name. They are the steady state solutions for the Fokker-Planck master equation. So basically pi here are Gaussian functions. They're Gaussians centered at the different values of the eigenvalues of the operator A. So basically, to get this, you have to do some sort of weighted average, where now you're averaging this. Actually, I think I have let me.
Yeah. So I mean, you essentially assume that
So for example, to derive that, we assumed a separation of time scale, and in that separation of time scale, we can actually see that we have a equilibrium distribution for D, because D is very fast. So D can keep up very fast with your measurement signal, and in that situation, pi's are this bunch of exponential, Gaussian functions around those values.
I see. Cool. Yeah. Thank you. That's interesting.
Thanks.
Guilherme, just to kind of tell you, some of people here, and I'm included among them, we are working on kind of coarse grain measurements, and maybe that's why, people are headed to these kind of beams, right? So, if you discretize your detector, it's not just the bandwidth, but like your precision on each beam would be kind of nearer or something like this, right? So, and we also do like we don't do any feedback, but it's like the inference that we have about our system description, right? Maybe that's where Carlos was heading, I'm not sure, just wild guess. Any further questions, comments? No? Okay, so if not, so then I'll thank Guilherme again for the very nice talk and to accept the invitation. It was very nice to learn about these results and to get to know you. So thank you a lot. And
thank you again, Fernando and Fred and everyone in this collaboration and all the people that attended here. For me, it was a pleasure and an honor to present my work here and to see there was some people interested in what we're doing. Thanks.
Sure. Thank you very much. So for that, I also like to thank the people at CBPF, so Ana and Rogério, for all the help with the infrastructure, so to say. So thank you very much. And with that, we finish here to the next seminar. Thank you very much.
Thank you.
Bye-bye, Guilherme.
Bye, Fred.
See you soon.
Yeah, thanks everyone. It was very good to see you. Bye, Guilherme, thank you for the talk. It was very good.
Thanks, Gabriel. Thank you for the questions. See you.
Bye-bye, Guilherme. Thank you so much. Thank you, everyone. Bye.
Bye, Paula.
Bye.
Eu acho que já não estamos mais no YouTube, né? Não. Ok. Bom, valeu, Ana. Valeu, Rogério. Obrigado aí. Acho que agora dá uma parada nas visitas, os visitantes chatos, coisas do tipo. Ok, começam as aulas, né? Então, vou parar de encher o saco. Valeu aí, obrigado. Tchau, tchau.
Nada. Tchau.